Welcome everyone. So in this video, I will talk about system behavior, system boundaries, and the relationship between these when it comes to system parts and how the system behaves as a whole. And the resource for this video is from a report by Hordar Haraldsson, which was published by Lund University in 2004, called Introduction to System Thinking and Causal Loop Diagrams. In the previous video from the, using the same resource, I talked more about linear thinking, and feedback loops, and the relationship with how we look at systems in general and systems thinking. So in this video, I will continue, talking about systems in particular, and also specifically, I will be focusing on systems, their parts, the system as a whole, and behavior itself, or the relationship with system behavior. So what is a system? According to Haraldsson, he looked at systems as a network of multiple variables that are connected to each other through a causal relationship and expresses some sort of behavior, which can only be characterized through observation as a whole. So, and in nature and in the human environment, everything is connected, everything is related to everything else in a complex web of interactions. And we can only understand the system dynamic behavior and interaction by viewing it as a whole, that is, viewing the system as a whole. So what kind of system are there? A very important question, a really good question. Basically, everything can be categorized and defined as a system. One way to describe a system is to review a technical one, which we can easily sort out. So Haraldsson used the example of a bicycle, which I will be using here as well, because it's very easy to grasp. So a bicycle can be considered as a system or a whole, where its functions depend on relationships between different parts, which are the frame, the chain of the bicycle, the wheels of the bicycles, the brakes, the lights, etc. And when you look at the bicycle in isolation, those components can never be identified as a bicycle if you take them apart, because the function of the bicycle is not embedded into individual components, but into the interaction or the relationships that we see between all of these components together. So a person that has never seen a bicycle before and sees one, looks at one lying, say, on the floor somewhere on the street, will never consider it other than a pile of metal, welded together. They will not grasp what it's supposed to do. Imagine, say you've got an alien that landed and looks at a bicycle and just look at it and think, what is this? What is a bicycle? So only if one sees someone riding a bicycle, then we will gain an understanding of the functionality. How does it function, as a system, from this whole heap of pile of metals and components welded together or put together, and connect the use of the system or the use of a bicycle in a broader term, in a broader sense, to transport, to leisure. So if you're an alien, you landed, you see a pile of parts put together, and you look at this thing called a bicycle. You don't know what it does, but then you see someone, a person, using that bicycle, and you see them. They're going from A to B. Then you start realizing, okay, so this person is using that bicycle for transport purposes. Maybe they're going to the gym, whatever it is. If you're that smart of an alien, you know what a gym is and what transport is. So as a result of that, we can only understand the behavior of the bicycle if we see someone riding it. So this is very important to keep in mind. So what is essential here becomes the bicycle rider, the person who rides the bicycle. Without this person, the behavior of the bicycle system doesn't really exist. It's not there. Okay, so, and now we have made that distinction. It's really important now that I've made that distinction between the parts of this bicycle and the whole, what the bicycle does, using that rider, that person who rides the bicycle. And it's in this interaction that you get a behavior, okay? Now, another really great example that is given here, and usually is given countless of times when we talk about systems thinking, is a forest. So if we take the example of a natural system, for example, in here, as I mentioned, a forest, we can't really analyze the forest just by looking at one tree, but we have to also consider other components, such as climate, animals, species, soil, topography, and so many other more components when it comes to a forest, which characterizes it and can therefore not be excluded if we want to understand a forest and how it functions as a whole, and even its behavior. So the tree by itself is a system that takes in nutrients, it takes water and exchanges gases. Along the trees stands, they stand fragile against the wind and rain. But collectively, as a whole, in a forest, trees change the evolution of the topography, the soil, the microclimates, and this is, as a result, leads to a behavior of a forest as a system. Also, if we take people and society, they are also considered a system as well, in a similar way to the forest. And then if we go up a notch, if we look at a city, we can also see cities as systems as well, as larger systems, and so on. So each one of these, we can look at every single thing as a system by itself. So we can state that when we use system thinking, we are really observing the dynamic relationship between all the parts within a system. The system is really steered by its feedback, and in order to understand the behavior of the system, we have to understand the feedback and also, importantly, the boundaries of the system. So all systems are defined by their boundaries. So for us to understand a system properly, we really need to understand how systems behave and also the properties of that system. Systems are usually confined by certain inflow and outflow of energy, which I also discussed before in separate videos. What makes it difficult sometimes is really to see a pattern that confines that system. For example, to determine where the boundaries are. So the principle of system thinking is that all behavior in a system is a consequence of its structure. The structure of a system determines its development. It determines whether it's successful or whether it fails. So naturally, to solve a problem within a system, it's usually right there. And because of that, going outside of it to look for a cause or a reason of the problem is either, Harlotson says, it's either erroneous or indicates that we need to expand our system boundaries in this case. We cannot solve all issues within our defined boundaries. That's the reason why, because we set certain system boundaries. This is because a system contains subsystems, and it is always embedded within a larger system. So this makes it really difficult because we set boundaries, and because of that, sometimes we are confined by these system boundaries, And if we want to go outside of these boundaries, then we need to look at other subsystems and go bigger, go larger. So let's take the example that Harlotson used. Another really useful example and a simple one to understand is a car. So, for example, as a car is considered a system by itself. It has special functions. The variables or the components of a car or a car system, let's call it, are the engine, the gearbox, the steering system, the tires, the electronics, and so on, and many other components. So what we consider as a car system, is really a sum of functions and interactions between all of these parts in the car. And the car maintains its functionality through feedback processes of all of its properly placed components that we studied, we understand for many, many years now, because we've been producing these cars for many years. Okay. We also know that the car will not operate properly if we take away some of these components. For example, its windows, its headlights, and so on. Its battery, obviously. This we know because we have, as Harlotson says, we have a fairly good understanding of how the car behaves as a system when we drive it. Not because we understand all the details of how the car is built, but how its system behaves. And the system boundaries for the car system here would be the physical structure itself, incorporating all of these components together. So it becomes simply the car system. So Harlotson says, how can we be sure that this would be our definition of the system, car, which is something that you might ask as well when you are trying to study research systems. How can you be sure that this would be your definition of the system as a car? So one way Harlotson says or suggests looking at it is to observe what goes in and out of that system that you are studying, that you are researching. Okay? So for the car system example, we know that the car is, in simple terms, it depends on fuel, it depends on oil, it depends on air, it depends on people. It transforms these materials through its system to exhausts, fumes, and also kinetic energy. What is important here to notice is that the car system doesn't depend on fuel or on oil from one geographical region per se, right? Or is restricted to exhausts, based on its fumes at a certain time or a certain location, right? These sort of aspects are not important. The car runs excellently as long as the criteria of how it functions, that is the feedback processes, the fuel, the air, the oil, are all met. So the system here is considered to be in balance when it's functioning. When you take the car itself as a boundary, the boundary is the car itself as using its physical components. That is the battery, the fuel, lodge, the engine, the windows, etc. Now, this is important. We could extend our system boundaries to incorporate now the fuel itself and air pollution. But then we would be increasing our system level observation, where we observe and study that system. So the car system in here, it becomes one variable, one subsystem of many in a larger system. And in this case, a system, if considered, could be called, it could be many different things. You could be observing or wanting to know about the fossil fuel system that really provides fuel for for the car, or you want to look at the air pollution system, because of the exhausts that comes out of the car. But in any way, these are all definitions that we set. This is very important. All of these definitions of systems, even if we expanded beyond the car system, what we define is really by us is setting boundaries. We are setting ourselves when we are observing certain aspects of reality. It's really how we are putting boundaries on those systems that we want to study that defines the system that we are looking at. And in a similar way, we could also go down, we could downsize our system boundaries and decide to analyze, for example, the battery in the car. The battery is a subsystem in the car system and can be also defined and confined by a system boundary that we're only looking at the battery itself, looking at its components or its variables, and in this case, they are water, acid, lead, copper, the structural organization of the container itself, and so on. Or it could be electric, electric car, and in this case, a different set of components, and so on. So in here, we are downsizing from the car system into a smaller subsystem. And also, we could also expand our system and what we consider and our boundaries even, we go the other way. We go into a city level, which is a large-scale system, where we are looking at resources and the energy into wastes and products through complex interactions of different variables in the city on an urban level or on a city level. So from all of these examples that I've just mentioned, from the car all the way to, an urban system, or even going down to a battery system, etc., when we are defining and confining a system, we need to understand its basic behavior, understand what is flowing in and out of the system, the physical units, or simply also the information flow that is happening. Then after that, we need to define the system level that we are observing. Is it on a molecular level? So really going down in the system into a minute quantum, say, level? Or are we going into a global scale or something in between? Does the system which you are observing move between different system levels? Does it do that? For example, are you dealing with local climate change in global perspective? This is what Haraldson explained. So I'll stop here and then I will continue in another video to make it much simpler and easier and talk about complexity in this case, system complexity that is, and then causal loop diagrams.